Algorithm accelerate in directions of consistent descent and dampen oscillations in areas where the gradient changes rapidly.
So it's like giving our hiker a little push to
Exactly.
help them maintain their momentum.
And avoid getting stuck in those small dips and
I
valleys.
can see how finding the right step size would be crucial too.
It is, and thankfully we have clever ways to adjust that step size or learning rate during training.
So it's like a smart hiking guide who adjusts the pace based on the terrain.
Right.
If the path is steep and rocky, we take smaller steps. If it's a gentle slope, we can lengthen our stride.
Exactly.
What are some of the other techniques for adjusting the learning rate?
Well, there's learning rate decay, where we gradually decrease the step size as training progresses.
Okay.
And then there are adaptive learning rate algorithms like ATOM and RMS prop, which automatically adjust the step size based on the history of gradients.
So it's like having a self-adjusting hiking boot.
I like that analogy.
That adapts to the terrain, so you don't have to manually change your step size.
Very cool.
It's amazing how much thought goes into designing these optimization algorithms and techniques.
It's a testament to the creativity and ingenuity of researchers in this field.
So we've talked about these algorithms that use the gradient to guide them down the lost surface.
Right.
Are there any algorithms that use more information than just the gradient?
Yes, there are algorithms that leverage more information about the lost surface. For example, the conjugate gradient method uses information about the curvature of the lost surface to take more informed steps.
So it's not just following the steepest descent.
Right.
It's taking into account the shape of the terrain.
Exactly. It's like having a topographical map that helps you navigate.
And then there are second-order optimization algorithms.
Yes, those use information about the second derivatives of the cost function.
Which tells us how the slope is changing.
Right.
So it's like having an even more detailed map.
With more precise information about the terrain.
But I imagine those second-order algorithms can get pretty computationally expensive.
Yeah, you're right, especially with deep neural networks that have so many parameters.
So are there any ways to make them more efficient?
Yes, the book discusses some approximations like the BFGS algorithm,
DFGS.
which tries to estimate the curvature information more efficiently. It's like having a rough sketch of the map instead of a high-resolution image.
Okay, so it's a trade-off between accuracy and efficiency.
Exactly.
What about things like parameter initialization and batch normalization? How do those fit into the optimization process?
Those are important considerations, too. Parameter initialization refers to how we set the initial values of the model's parameters before we start training.
Does it really matter where we start?
It can make a big difference. Think of it like this. If you start your hike at the bottom of a deep, narrow canyon, it's going to be a lot harder to reach the summit than if you start on a more open, gradual slope.
So we need to give our optimization algorithm a good starting point.
Exactly, but not just airlift it to the summit.
All right, we want it to learn the terrain as it goes.
The book talks about strategies like initializing the weights randomly from a Gaussian.
Giving our hiker a random starting point on the mountain,
Right,
but making sure they're not too far from base camp.
exactly.
What about batch normalization?
Batch normalization is a technique that normalizes the activations of each layer during training.
Okay.
This helps to stabilize the learning process and can lead to faster convergence.
So it's like making sure all the hikers in our group are on the same page.
Yeah, that's a good way to put it.
Making sure everyone's moving at a similar pace and in the right direction.
Exactly. It helps to keep the optimization process running smoothly.
It's fascinating how much thought goes into designing these optimization algorithms and techniques.
It's like we're building these sophisticated tools to navigate the complex landscapes of deep learning.
And it's not just about finding the best solution for a specific problem.
Right.
It's about understanding the general principles of optimization.
That can be applied to a wide range of machine learning tasks.
That's really cool.
And the book even explores some fascinating ideas about how we can shape the optimization landscape itself.
Shape the landscape.
Yeah, making it smoother and easier to navigate.
How do we do that?
Well, one approach is called continuation methods.
Continuation methods.
The idea is to solve a series of progressively harder optimization problems,
Okay.
starting with an easy one and gradually increasing the difficulty.
So it's like starting with a gentle hike on a well-marked trail
Right.
and gradually progressing to more challenging routes.
Exactly, as you gain experience and confidence.
So we're easing the model into the complexity.
Yeah, kind of like a warm-up routine for a marathon runner.
What other techniques are there for shaping the learning process?
Another fascinating approach is curriculum learning.
Curriculum learning.
This takes inspiration from how humans learn, We don't throw the most difficult concepts at students right away.
No, we start with the basics.
Right, and gradually increase the complexity as they build their understanding.
Like learning the alphabet before tackling Shakespeare.
Exactly. And in curriculum learning, we do the same thing with our deep learning models.
We start with easier examples
Right.
and gradually introduce more difficult ones.
It can help the model learn more efficiently and avoid getting overwhelmed.
So it's like having a personalized tutor for our model,
I like that analogy.
guiding it through the learning process.
This whole chapter on optimization has been like a masterclass in problem solving.
It really has.
It's amazing to see how much ingenuity goes into designing these algorithms and techniques.
That enable these powerful models to learn and improve.
And it's just one chapter in a book filled with insights and discoveries.
I know.
What's really striking me is how deep learning blends cutting-edge technology with these fundamental principles of learning and optimization.
Yeah, it's not just about brute force computation.
No, it's about understanding how these systems learn.
And how to guide them effectively.
And that's what makes this field so exciting.
I completely agree.
What are your thoughts so far?
I'm really amazed by how much we've learned just in these first few chapters.
Me too.
It's like we're witnessing a new kind of intelligence emerge.
And understanding how it works is both fascinating and a little bit awe-inspiring.
It is awe-inspiring.
And a little bit humbling, too, to realize how much we still don't know.
But that's what makes this journey so compelling.
Absolutely. There's so much more to explore.
What adventures await us in the next chapter?
Well, that's where things get really visual. We're diving into the world of convolutional neural networks, the rock stars of computer vision. Get ready to see how deep learning is revolutionizing the way computers see and understand the world around us.
Welcome back to the Deep Dive. We've gone through the foundations of deep learning, explored how to keep our models in check with regularization, and delved into the fascinating world of optimization algorithms.
And now get ready to see, because we're stepping into a world where computers learn to see.
Ooh, with convolutional neural networks.
That's right. Convolutional neural networks, or CNNs for short. They are the undisputed champions in the domain of computer vision. They've revolutionized how computers understand images, and they enable applications like facial recognition, object detection, self-driving cars, even medical image analysis. It's pretty remarkable.
I've always been so fascinated by how CNNs can actually make sense of visual information, especially considering how complex and nuanced our own visual perception is as humans. What makes them so good at this?
Well, CNNs are specifically designed to exploit the spatial structure of images. They use a clever mechanism called convolution.
Convolution.
Which you can think of as like a sliding window that moves across the image, extracting features from local regions.
So instead of treating the image as a giant grid of pixels, a CNN breaks it down into smaller, more manageable chunks.
Exactly. And the beauty of convolution is that it allows the network to learn features that are invariant to location.
Invariant to location.
Meaning if a CNN learns to detect a cat's ear, it can recognize that ear whether it's at the top of the image, the bottom, or anywhere in between.
So it's like having a built-in understanding of how objects can exist in different parts of an image without changing their identity.
Right. That's one of the key insights behind CNNs.
That's pretty impressive. What other tricks do CNNs have up their sleeves?
Well, they leverage two key ideas that are crucial for their success. Sparse interactions and parameter sharing sparse interactions mean that each neuron in a convolutional layer is only connected to a small region of the input. This makes the network more efficient and allows it to focus on local details.
It's like having a detective examine a crime scene and focusing on specific areas of interest rather than trying to take in the entire scene all at once.
Exactly, great analogy. And then parameter sharing means that the same set of weights is used across different spatial locations in the image.
So it's like having a universal feature detector.
Right.
That can spot a cat's ear regardless of where it's located in the image.
Precisely, and this combination of convolution, sparse interactions, and parameter sharing makes CNNs incredibly powerful for image recognition tasks.
So the book kind of walks us through the architecture of a typical CNN.
It does. It explains the role of convolutional layers, pooling layers, and fully connected layers.
Okay, so let's break that down. What do those different layers actually do?
Sure. So convolutional layers, as we've discussed, they perform that convolution operation, extracting features from local regions of the input.
Okay.
Pooling layers downsample the feature maps, reducing their size and making the network more robust to variations in the input.
Robust to variations.
Like small changes in position or scale.
Gotcha.
And fully connected layers, which we encountered before in feed-forward networks, they combine those learned features and make the final predictions.
It's like having a team of specialists, each responsible for a specific part of the image analysis process.
I like that.
Yeah, like the convolutional layers are the detectives gathering clues from the scene. The pooling layers are the analysts sifting through the evidence and identifying the most salient points. And the fully connected layers are the judges making the final verdict based on all the presented evidence.
That's a fantastic analogy. It really captures the essence of how these different layers work together.
And the book doesn't just describe the architecture. It dives into the details of how these networks are trained, highlighting the role of backpropagation.
Right, backpropagation is still the key.
So even though CNNs have this specialized architecture for handling images, the fundamental principles of learning and optimization still apply.
Absolutely. Backpropagation is that engine that drives the learning process, regardless of the network's architecture. It's the feedback loop that tells the network how to adjust its weights to get better at its task.
It's like having a coach who analyzes the team's performance and gives them feedback on how to improve their game.
Exactly. A very important part of the training process.
The book also explores some of the challenges and considerations for training CNNs, such as choosing the right activation function, preventing overfitting, and selecting an appropriate optimization algorithm.
Right. Those are all important factors that can affect the performance of the network.
It's like being a craftsman, carefully selecting the right tools and techniques for the job.
Deep learning is not just about applying a one-size-fits-all solution. It's about understanding the nuances of these models and tailoring them to the specific task at hand.
It's about being thoughtful and adaptable.
Exactly.
So Chapter 8 takes us beyond just image recognition into the world of sequence data.
Right. Chapter 8 introduces recurrent neural networks, or RNNs.
RNNs.
Which are specifically designed to handle sequential data, like text, speech, time series, you name it.
So anything where the order of the data matters.
Exactly. They have this amazing ability to remember information from previous time steps, allowing them to understand context and make predictions based on sequences of events.
It's like having a memory that can retain information over time.
Right.
Allowing you to understand a story as it unfolds or predict the next word in a sentence.
Exactly. RNNs are all about understanding sequences and patterns over time.
That's really cool. How do they achieve this memory-like capability?
Well, the key lies in their recurrent connections, unlike feed-forward networks, where information flows in one direction. RNNs have connections that loop back on themselves, allowing information to persist from one time step to the next.
So it's like having a feedback loop within the network.
Exactly, allowing it to retain information from the past.
The book delves into the architecture of a typical RNN and explains how the hidden state acts as this memory.
Right.
And is updated at each time step based on the current input and the previous hidden state.
It's a beautiful example of how a simple yet elegant design can lead to some really powerful capabilities.
It's like having a notebook where you keep writing down your thoughts and ideas, and each new entry is influenced by what you've written before.
I like that analogy.
But handling sequences can be tricky, right?
Yeah.
I imagine there are some unique challenges specific to RNNs.
Oh, there are, definitely. And the book doesn't shy away from those challenges. One major challenge is the vanishing gradient problem.
The vanishing gradient problem.
Which can make it difficult for RNNs to learn long-range dependencies.
So events that happened a long time ago might fade from the network's memory.
Right. It's like trying to remember something that happened years ago.
Yeah, the details get fuzzy.
Exactly. And to address this challenge, researchers have developed specialized types of RNNs, like long short-term memory networks, or LSTMs, and gated recurrent units, or GRUs.
Okay, those sound familiar.
Yeah, they've become very popular and effective, and they have mechanisms to selectively remember or forget information, allowing them to capture both short-term and long-term dependencies.
So it's like having a more sophisticated note-taking system.
Right.
Where you can highlight important information, annotations, even tear out pages that are no longer relevant.
Exactly, a very smart notebook.
Yeah.
And the applications of RNNs are expanding rapidly. The book touches on some of those exciting developments, from natural language processing to machine translation to speech recognition, and it's clear that RNNs are playing a pivotal role in shaping the future of artificial intelligence.
So Chapter 9 kind of takes us beyond these specific architectures and challenges us to think about the bigger picture of deep learning.
Right. Chapter 9 shifts our focus from the nuts and bolts of models and algorithms to those broader questions of what deep learning means and where it's headed.
So where is it headed?
Well, the book explores this concept of representation learning.
Representation learning.
The idea that the key to building intelligent systems is to learn good representations of data.
So it's not just about crunching numbers, it's about finding meaningful ways to represent information.
Exactly. Think about how we humans represent the world around us. We don't just store raw sensory data in our brains.
Right, we formed concepts and categories.
We create abstract concepts, categories, relationships that help us make sense of it all.
It's like creating a mental map of the world.
Yes, with landmarks, routes, and connections that help us navigate and make sense of our surroundings.
So deep learning is trying to do the same thing.
In a sense, yes, it's trying to learn representations that capture the essence of the data, allowing for generalization and understanding.
It's like giving these machines a language to understand the world.
That's a great way to put it. And the book highlights the remarkable progress that's been made in representation, learning from learning features that can distinguish cats from dogs to learning embeddings that capture the meaning of words and sentences.
That's really cool. It's like we're unlocking the secrets of how meaning is encoded in data.
Exactly. And as we move forward, one of the key challenges for deep learning is to learn even richer, more abstract representations, representations that capture not just perceptual features, but also concepts, relationships, even causal structures.
It's like moving from recognizing objects to understanding how they interact and influence each other.
Exactly. It's like piecing together a complex puzzle where each piece reveals a new layer of understanding.
That's a really cool way to think about it. So as we wrap up our exploration of this book, what are some of the key takeaways and insights that you think are most important for our listeners?
Well, I think this book does a remarkable job of capturing the essence of deep learning, its history, its challenges, its triumphs, and its vast potential. It's a testament to the brilliance and dedication of all the researchers who have pushed the boundaries of this field, and it's an invitation for all of us to join in on this incredible journey of discovery.
I completely agree. I'm walking away with a newfound appreciation for the complexity, the ingenuity, even the beauty of this field. It's really amazing how much progress has been made, and it's exciting to think about what the future holds as deep learning continues to evolve and mature.
Absolutely. And I think this book is a great starting point for anyone who wants to learn more about this fascinating field.
So if you're intrigued by what you've heard today, we highly recommend checking out the book Deep Learning by Ian Goodfellow, Yoshua Bengio, and Aaron Corville.
It's a comprehensive and insightful guide to this rapidly evolving field.
And on that note, we'll wrap up this episode of The Deep Dive. Until next time, keep those brains curious and those learning algorithms humming.